Right now, you feel time moving. You feel the present moment as something real, something solid, something you are standing inside of. A second ago is gone. A second from now has not arrived. And here you are, locked in the now, riding a river that only flows one way. That feeling is so fundamental, so deeply wired into every thought you have ever had, that questioning it feels almost like a joke. But here is what the smartest people on Earth have discovered after a century of the most precise experiments ever conducted. That feeling is wrong. Not slightly wrong, not philosophically wrong, but physically, mathematically, experimentally wrong. The river does not flow. Time does not pass. Your past, your present, and your future may all exist simultaneously in a structure so alien to human intuition that physicists struggle to find words for it. And the moment that has not happened yet, the moment of your death, may already exist, frozen and waiting, as real as the chair beneath you right now. This is not a thought experiment. This is where the physics leads. And it is terrifying. There is a moment happening right now. You are inside it. You can feel it. The present moment surrounds you like a room, and you are standing at its center, fully aware that what just happened is behind you and what is about to happen is ahead of you. This feeling is so immediate, so undeniable, so woven into the texture of your consciousness that it barely registers as a belief. It feels more like a direct observation, like touching a hot stove and feeling the heat. You are not theorizing that the present exists. You are experiencing it. And that is exactly the problem. Because when physicists and neuroscientists began examining the machinery behind that experience, they found something deeply wrong with it. Not slightly off, not a matter of philosophical interpretation, but structurally, mechanically, measurably wrong. The sensation of being inside a flowing present moment, the feeling that time is moving, that now is special and real in a way that yesterday is not, turns out to be a construction, a story your brain tells you, a user interface assembled from fragmented signals, stitched together with a half-second delay, and presented to your consciousness as something it is not. We need to start here, at this exact point of discomfort, because everything that follows depends on understanding one foundational truth. The experience of time is not the same thing as time itself, and the gap between those two things is so enormous, so vertiginous, that once you see it clearly, you will never be able to look at a clock the same way again. Let us start with something that sounds simple. What is the present moment? Right now, as you are watching this, you feel like you are experiencing the world in real time. Light hits your eyes, sound hits your ears, and you perceive it all simultaneously, a unified snapshot of the current instant. But your brain is not doing that. Your brain is doing something far stranger. Light travels faster than sound. By an enormous margin, when something happens in front of you, the light carrying the visual information reaches your eyes almost instantly, but the sound of that same event arrives a fraction of a second later. And yet, you do not perceive a gap. You do not see the explosion and then hear it separately inside your skull. Your brain waits. It buffers the incoming information, holds it in a kind of short-term queue, and then assembles it all into a single coherent experience that it labels now and delivers to your consciousness as a unified moment. Neuroscientist David Eagleman, who has spent decades studying the timing of perception, has demonstrated this with extraordinary precision. His research shows that what we experience as the present moment is not actually the present at all. It is the recent past. Your brain is constructing an experience of now that is somewhere between 80 milliseconds and half a second behind the actual moment of the physical events that triggered it. By the time you consciously perceive something happening, it has already happened. The now you are experiencing is a memory of an event that has already passed. This should already disturb you. The most immediate, most certain thing you have access to, the present moment, is a reconstruction assembled after the fact by a biological machine that is doing its best to present a coherent narrative. You are not watching live television. You are watching a broadcast with a delay, and the delay is being hidden from you so seamlessly that you never notice it. But this is only the beginning of the strangeness, because the brain does not just delay information, it actively edits it. It smooths over inconsistencies, it fills in gaps, it makes retroactive corrections to the timeline of events. Eagleman and his colleagues conducted an experiment in which subjects were shown a flash of light followed by a beeping sound. When the sound came slightly after the flash, subjects perceived them as simultaneous. The brain had quietly erased the gap. It had decided that simultaneous made more sense as a narrative and had rewritten the history of the last half second accordingly. Think about what that means. Your brain is not just constructing the present moment with a delay. It is actively rewriting the recent past to make your experience of the present more coherent. The timeline you experience is not the timeline of events. It is an edited version, processed, corrected, and smoothed by a system that prioritizes narrative consistency over raw accuracy. This is not a flaw. This is a feature. Your brain evolved under intense pressure to make rapid decisions. Spending cognitive resources on the true temporal sequence of microscopic events would be catastrophically inefficient. So evolution built a system that approximates, that guesses well enough, and that presents the result as if it were direct perception. You are not experiencing reality. You are experiencing your brain's best reconstruction of reality, presented to you with the editorial seams hidden. Now here is where the ground starts to genuinely shake. Because all of this, the delay, the editing, the construction of the present moment, this is just the neuroscience. This is what is happening inside your skull. When you step outside the skull and look at what physics says about time, you find that the problem runs far deeper. You find that it is not just your brain that is confused about the present moment. It is the universe itself that refuses to supply one. In 1905, a 26-year-old patent clerk named Albert Einstein published a paper that quietly dismantled one of the most fundamental assumptions in the history of human thought. The assumption was this: that time is universal, that there is a single cosmic clock ticking at the same rate everywhere, and that the word now means the same thing for every observer in the universe, regardless of where they are or how they are moving. This assumption is so deeply embedded in our intuition that it almost sounds ridiculous to question it. Of course, now means the same thing for everyone. It is now. It is happening. It is the present. Whether you are standing on Earth or floating in a spacecraft, whether you are moving fast or slow, the current moment is the current moment. How could it be otherwise? Einstein showed how. He started from a simple, experimentally verified fact. The speed of light in a vacuum is the same for every observer, regardless of how fast they or the light source are moving. This sounds like a boring technical detail about physics. It is actually the detonator of a conceptual bomb. Imagine two observers. One is standing on a train platform. The other is sitting in the center of a train car, moving past the platform at an enormous fraction of the speed of light. At the exact moment the moving observer passes the center of the platform, lightning strikes both ends of the train simultaneously, from the perspective of the person on the platform. Two bolts, left end and right end, at exactly the same time. The person on the platform sees both flashes at the same moment and correctly concludes they were simultaneous. But now consider the person on the train. The train is moving toward the front bolt and away from the rear bolt. Since the speed of light is constant for all observers, the light from the front bolt reaches the moving observer first, before the light from the rear bolt arrives. The moving observer, following the same logic and the same physics, concludes that the front bolt struck before the rear bolt, not simultaneously at all. Who is right, Einstein's answer was the most destabilizing thing anyone has ever said about reality. Both of them are right. There is no fact of the matter about whether the two bolts were simultaneous. Simultaneity is not an objective feature of the universe. It depends entirely on the state of motion of the observer. Two events that are simultaneous for one observer are not simultaneous for another observer moving relative to the first, and neither of them is making a mistake. This is not a matter of one observer having incomplete information. It is not a case where the true answer exists and one person simply does not know it. The relativity of simultaneity is built into the structure of space-time itself. There is no universal now. There is no master clock ticking in the background that all observers could in principle synchronize with. The present moment, the very concept of now, is local, personal, and relative to your state of motion. Let the full weight of that land. Right now, as you are watching this, there are other observers in the universe moving relative to you. Maybe not dramatically, but anything counts. Even two people sitting in different vehicles moving at slightly different speeds are, strictly speaking, experiencing different nows. Events that are simultaneous in your reference frame are not simultaneous in theirs, not because of a limitation in their perception, not because of the delay in light reaching them, but because of the geometric structure of reality itself. This means that the question of what is happening right now across the universe has no single correct answer. An astronaut on the International Space Station, moving at roughly 7.7 kilometers per second relative to people on the ground, is living in a slightly different slice of space-time. Their now is not your now. And if you imagine an observer moving at a significant fraction of the speed of light relative to Earth, the discrepancy becomes enormous. Events that have already happened for you might be in their future. Events that have not happened yet for you might already be in their past. This is not science fiction. This is the experimentally confirmed structure of space-time. And it has a consequence that most people never follow through to its logical conclusion. If there is no universal now, if different observers in relative motion have fundamentally different presence, then the division of time into past, present, and future is not a feature of the universe. It is a feature of your particular location and velocity. It is a property of your reference frame, not of reality. And yet, we experience time as having this absolute, undeniable directionality. We experience the present as categorically different from the past and the future. We experience ourselves as moving through time, as being inside the current moment rather than some other moment. Why does time feel so powerfully, so irresistibly sequential, if the physics says sequence is relative? This is where we return to the brain, but at a deeper level. Your brain evolved on the surface of one planet, at one particular location in space-time, moving at speeds so far below the speed of light that relativistic effects on simultaneity are completely negligible for any practical purpose. The relativity of simultaneity affects objects moving at thousands of kilometers per second relative to each other. Your morning commute does not expose you to those conditions, so your brain never developed any intuition for it. Your entire sense of flowing time, of the present being special and real, of the past being fixed and the future being open, was built by evolution to navigate a world where Newtonian mechanics provides a close enough approximation to reality. The sensation of now, the feeling of being inside the current moment, is an interface. It is a simplified representation designed for survival, not for accuracy. Think about what it would actually feel like to perceive time the way physics describes it. You would need to be aware that your present moment is your own local reference frame construct. You would need to hold in mind that observers elsewhere in the universe have a different now. You would need to perceive the relativity of simultaneity as a visceral feature of every interaction with the world. You would, in short, be unable to function. Your brain would be overwhelmed by information it has no way to use for the purpose of finding food, avoiding predators, and raising children. So it's simplified. It built the experience of an absolute present. It built the sensation of time flowing. It made past and future feel categorically different. And it presented all of this to you not as a model but as direct perception, so that you would never waste energy questioning it. Donald Hoffman, the cognitive scientist whose work on the interface theory of perception has generated enormous discussion in the physics and philosophy community, has described this process with a devastating metaphor. The icons on your computer desktop, the little folder icons, the trash can icon, these are not what the files actually look like. There are no little blue rectangles inside your hard drive. There is no miniature trash can. The icons are a simplified, user-friendly interface that hides the actual structure of the underlying system, which would be incomprehensible if displayed directly. You interact with the icons and the system works, but the icons are lying to you about the nature of the reality they represent. Your experience of time is an icon. The sensation of flowing from past through present into future is a desktop representation of something whose actual structure is radically different from anything your intuition can grasp. The icon is useful. It allows you to plan, to remember, to anticipate. But it is not accurate. And the moment you start taking the icon literally, the moment you start believing that the present moment as you experience it reflects a real feature of the universe, you have made the same mistake as a character in a video game who believes the map of their world is the world. Now, this idea that the present is a construction, that now is a local phenomenon rather than a universal one, that time as we experience it is a biological and cognitive interface rather than a direct perception of reality. This is disturbing, but it is not yet the full depth of the problem. It is the first layer. The discovery that unsettles you before the real unsettling begins. Because what we have established so far still leaves room for a comfortable interpretation. You might tell yourself, okay, the present moment is a construction of my brain, and it differs slightly between observers in relative motion. But surely the sequence of events is still real. Surely cause and effect still hold. Surely time still flows, even if the precise definition of now is fuzzy at the edges. But this comfort is precisely what the rest of this story is going to dismantle. Because Einstein's discovery was not just about the relativity of now, it was about the structure of time itself. And the deeper you go into that structure, the more the comfortable picture dissolves. The relativity of simultaneity does not just mean that different observers disagree about which events are happening at the same time. It means that the entire separation of space-time into past, present, and future is observer-dependent. Events that are in your future might be in another observer's past, not metaphorically, not due to limited information. Physically, geometrically, in terms of the actual structure of space-time, this is the foundation on which the block universe stands. And the block universe is where the story truly becomes terrifying. But before we go there, we need to sit with what we have already found, because it deserves more than a quick acknowledgement. We have established that the experience of the present moment is a neural construction with a measurable delay. We have established that this construction involves active editing of the recent past. We have established that evolution built this interface not to show you the truth about time, but to allow you to function effectively in a low-velocity Newtonian environment. And we have established that the physics of that same universe reveals, with experimental precision, that simultaneity is relative, that there is no universal now, and that the present moment as a feature of reality itself is not coherent across different reference frames. What this means is that the most certain, most immediate, most unavoidable feature of your experience, the fact that you are here, now, in this moment, alive and aware, is built on a foundation that the universe itself does not supply. The universe does not provide a present moment. Your brain provides it. and your brain is providing it using a set of rules that were optimized for a world where time's true nature would never need to be confronted. There is something almost elegant about this. The universe built creatures whose survival depends on a simplified model of time. Those creatures used that simplified model to develop science. That science eventually revealed that the model is wrong. And now those creatures are standing at the edge of what their own evolved cognitive interface can perceive, looking out at a structure so alien that they can only describe it in mathematics because their direct experience gives them nothing useful. You are one of those creatures. And you are doing exactly that. Standing at the edge, looking out, feeling, perhaps for the first time, that the room you have been standing in, the present moment you have been living inside, is not a room at all. It is a painting of a room. It is a projection. And just beyond the edges of the canvas, the actual structure of time waits, cold and geometric and completely indifferent to your intuition about it. The brain builds the present moment from scattered signals and a deliberate delay. Physics refuses to supply a universal present at all. Together, these discoveries do not just challenge our understanding of time, they challenge the most basic framework through which we understand what it means to exist. You are not standing in the now. You are standing in your brain's most recent rendering of a recent past that has already happened, inside a reference frame that is yours alone, inside a universe that does not recognize the concept of now as anything more than a local, observer-dependent artifact. That is where we begin. That is the crack in the foundation. And the crack goes all the way down because once you understand that the present moment is not what it seems, you are ready for the next discovery. The discovery that shook Einstein to his core. The discovery that time does not just vary between observers at the level of simultaneity. It physically slows down and speeds up depending on how fast you move and how deep you are in a gravitational field. And the experiments that prove this were not performed in theoretical papers. They were performed with real clocks, on real airplanes, in real satellites orbiting the real Earth. Time does not just feel different for different observers. It runs at genuinely different rates. It is physically elastic, and the consequences of that elasticity reach far beyond the laboratory. They reach into the very structure of what exists, what has existed, and what will exist. They reach into the question of whether the future is real right now, whether it is already out there waiting for you, already fixed and completed in the geometry of space-time. They reach into the question that will be with you for the rest of this story. The question that Einstein called the most stubborn illusion. The question of whether time, as you experience it, as you live inside it, as you trust it to carry you from moment to moment through your life, is actually there at all. In 1971, two physicists named Joseph Hafele and Richard Keating did something that would have been considered absurd a century earlier. They bought airplane tickets, 4 of them flying on commercial passenger jets, circumnavigating the globe. They were not traveling for a conference. They were not visiting family. They brought with them a set of extremely precise atomic clocks, the most accurate timekeeping instruments that existed at that moment in history. They flew east, then they flew west. And when they landed and compared their airborne clocks against identical clocks that had remained stationary on the ground, the clocks disagreed. Not by a lot. The differences were measured in nanoseconds, billionths of a second. But the disagreement was real, measurable, and it matched Einstein's predictions with extraordinary precision. The clocks that had been moving through the air had experienced time differently from the clocks that had stayed still. Not because the clocks were broken, not because of vibration or temperature or any mechanical interference, but because time itself had passed at a genuinely different rate for the moving clocks than for the stationary ones. This experiment was not the first confirmation of its kind, and it was not the last, But there is something particularly visceral about it, because those clocks flew on ordinary commercial airplanes. They flew at ordinary cruising altitudes, at ordinary flight speeds. The passengers sharing the cabin with those clocks, reading their newspapers and eating their meals, were aging at a slightly different rate than the people they had left behind on the ground, by an almost incomprehensibly small amount, but by a real amount, measured, verified, written in the data. Time dilation is not a theoretical curiosity. It is a physical fact that has been confirmed by dozens of independent experiments, from the decay rates of particles produced in accelerators to the corrections that must be applied to the satellites of the global positioning system every single day. And to understand why it happens, why motion through space genuinely stretches time itself, we need to go back to the insight that Einstein arrived at in 1905 and follow it to its conclusion without flinching. We established in the previous section that the speed of light is constant for all observers, regardless of their motion. Einstein took this fact seriously in a way that nobody before him had dared to. He asked what the universe must be structured like in order for this to be true. And the answer he found was that space and time cannot be independent. They have to be connected. They have to be two aspects of a single four-dimensional fabric that he called space-time. And within that fabric, speed through space and speed through time are not independent quantities. They trade off against each other. Here is the core of the idea. Every object in the universe is always moving through space-time at the same total speed. Always. There are no exceptions. That total speed is the speed of light. But the speed of light can be divided between two components: motion through space and motion through time. If you are sitting completely still in space, if you are not moving in any spatial direction at all, then your entire velocity through space-time is directed into the time dimension. You are aging as fast as it is physically possible to age. Time is passing for you at its maximum rate. Now you start moving through space. You are still traveling through space-time at the speed of light, but now some of that velocity is directed into the spatial dimensions. That means less of it is directed into the time dimension. Your clock slows down, not from your own perspective. From your own perspective, time always feels normal, but from the perspective of an observer who is moving differently from you, your clock is genuinely ticking more slowly. And the faster you move through space, the slower you move through time. This is time dilation. And it is not a measurement error. It is not an illusion. It is the actual physical slowing of time for objects in motion relative to other objects. The clocks on the Hafele-Keating airplanes were moving through space at a few hundred meters per second relative to the ground clocks. That is a tiny fraction of the speed of light. The time dilation effect was correspondingly tiny, measured in nanoseconds. But the effect was real. And at speeds approaching the speed of light, the effect becomes dramatic. Consider the twin paradox, one of the most famous thought experiments in physics. Take two identical twins, put one of them on a spacecraft, accelerate that spacecraft to a substantial fraction of the speed of light, say 80%, and send it to a nearby star system about 10 light years away. Then bring it back. The traveling twin returns to Earth. The twins stand next to each other. They look at each other, and one of them is dramatically younger than the other. Not metaphorically, not in terms of how they feel or how they look. In terms of actual elapsed biological time, the number of heartbeats that have occurred, the number of cell divisions that have taken place, the amount by which each twin has physically aged. The twin who traveled at high speed through space has aged less, significantly less, years less. From the ground twin's perspective, the journey took about 25 years. From the traveling twins' perspective, because their clocks were running slower due to their high velocity, the journey took considerably less time, perhaps only around 15 years, depending on the exact parameters. These two people, who were born at the same moment are now different ages, not because of anything biological, because time passed at different rates for them, because time is not a fixed backdrop, it is a flexible dimension, and its flow rate is determined by the geometry of your path through space-time. The twin paradox sounds like science fiction. It sounds like something that could not possibly have real-world consequences, but it does. Right now, above your head, there are dozens of GPS satellites orbiting the Earth. Each of those satellites carries an extremely precise atomic clock. Your phone uses the signals from those clocks, comparing timestamps, to calculate your position to within a few meters. But here is what most people do not know. The clocks on those satellites run at a different rate than the clocks on the ground. Not by much, but enough to matter enormously if left uncorrected. The satellites are moving at high speed relative to the ground, which means special relativity causes their clocks to tick more slowly. But the satellites are also much farther from Earth's gravitational field, which means general relativity causes their clocks to tick faster. Yes, faster. And this introduces the second dimension of time dilation, the one that Einstein derived a decade after his special theory, and the one that is arguably even more mind-bending than the first. Gravity, Einstein discovered, is not a force in the classical sense. It is not an invisible hand reaching across space and pulling objects toward each other. It is the curvature of space-time itself caused by the presence of mass and energy. Massive objects bend the fabric of space-time around them, and objects moving through that curved fabric follow the curves. What we experience as the gravitational pull of the Earth is simply the natural path of objects through the curved space-time that Earth's mass has created. This might sound like a semantic distinction, but it leads to a consequence that is staggering. If gravity is curvature of space-time, and if the curvature is steeper, closer to a massive object, then time itself is distorted by gravity. Time runs more slowly in a stronger gravitational field. The deeper you are in a gravitational well, the more space-time curves around you, and the more slowly your clock ticks relative to clocks further from the mass. On the surface of the Earth, you are deeper in Earth's gravitational well than someone standing on a mountaintop. That person on the mountaintop is aging, very slightly, faster than you. Not because of anything about their biology, because time is literally passing more quickly at higher altitude. The difference is tiny at the scale of mountains, but it is real. It has been measured. In 2010, physicists at the National Institute of Standards and Technology used aluminum-ion clocks precise enough to detect the difference in clock rates between two heights separated by just 33 centimeters, less than the height of this document. And they measured it. Gravitational time dilation is so real that it operates at the scale of a foot of elevation difference. Now scale this up. Near a very massive object, the effect becomes enormous. Near a neutron star, where a teaspoon of material weighs as much as a mountain range, time runs dramatically more slowly than it does in open space. Near a black hole, the curvature of space-time becomes so extreme that the slowing of time near the event horizon becomes absolute. For an observer falling toward a black hole, time passes normally. But for someone watching from a safe distance, the falling observer appears to slow down, their image frozen and red-shifted, their clock essentially stopping as they approach the horizon. From the outside, they never quite cross it. From their own perspective, they cross it in finite time and continue falling. Two clocks, the same event, two completely different durations. This is not a paradox, this is the structure of reality. The GPS satellite system handles this constantly. The satellite's clocks run slow due to their orbital velocity by about 7 microseconds per day. They run fast due to their distance from Earth's gravity well by about 45 microseconds per day. The net effect is that they gain approximately 38 microseconds per day relative to clocks on the ground. 38 microseconds sounds trivial, but GPS works by measuring incredibly precise time differences in signal arrivals. An error of 38 microseconds per day would accumulate into a positional error of about 10 kilometers per day. Within hours of ignoring relativity, the GPS system would become useless. The engineers who built it had to bake Einstein's equations into the fundamental design of the satellites, correcting for the different rates of time at different altitudes and velocities. Every time you use navigation on your phone, you are relying on Einstein's discovery that time passes at different rates in different places. Let that settle for a moment. The device in your pocket, the one you use to find a restaurant or navigate to a friend's house, only works because the engineers accounted for the fact that time passes at different rates in different parts of space. Relativity is not abstract. It is infrastructure. But here is where we need to push past the practical applications and follow the physics into more unsettling territory. Because Rovelli and Keating, the GPS system, the twin paradox, all of these are demonstrations of the same fundamental truth. Time is not a fixed, universal constant. It is a dimension of space-time, and like spatial dimensions, it can be stretched, compressed, and curved by mass, energy, and motion. Different parts of the universe are genuinely aging at different rates right now. The center of the Earth, deep in our planet's gravitational well, is measurably younger than the surface. The surface of the Sun is aging more slowly than the space above it. Near a black hole, time crawls to near stillness while the universe outside races forward. This is not a metaphor. This is geometry. And when you follow this geometry to its logical conclusion, you arrive somewhere deeply strange. Because if time can be stretched and compressed and curved, if its rate of flow depends on your location and velocity, then what exactly is time? What is it made of? What does it mean to say that time passes? In classical physics, and in everyday human experience, time is assumed to be a kind of river. It flows in one direction. It carries you forward. The past is upstream, already traveled and fixed. The future is downstream, not yet reached. The current moment is where you are right now. The only place where anything is actually happening. The only slice of existence where the universe is alive and real. Now, let us push past the engineering applications and confront what the physics is actually telling us at a structural level. Because the Rovelli-Keating experiment, the GPS corrections, the twin paradox, these are not isolated curiosities. They are converging on a single uncomfortable truth. Time is not a fixed backdrop against which the universe performs. It is a dimension, flexible, stretchable, curvable, woven into the fabric of space-time itself. And different regions of that fabric are genuinely experiencing different rates of its passage right now. There is no master clock. There is no universal time. There is only the geometry of space-time, curved by mass and stretched by motion, with every clock reading out its own local version of time's passage. And no way, in principle, to determine which is the true rate, because there is no true rate. There is only the local rate, and the local rate depends entirely on where you are and how fast you are moving. The clock on the airplane returned showing a different time. The twin who traveled came back younger. The GPS satellites require daily correction or your phone sends you to the wrong street. None of this is consistent with a universe where time is a fixed, universal river. All of it is perfectly consistent with a universe where time is elastic, where its rate of passage is a local geometric property rather than a universal feature, and where the question of what is happening right now depends entirely on your position and velocity in the four-dimensional fabric. And once you accept that time is a geometric dimension, stretchable and curvable like space, the structure of that geometry begins to point toward a conclusion about the nature of the future, about what exists and what does not. that the mathematics states clearly and that intuition refuses with everything it has. It is a conclusion that sits waiting at the end of the next step, and it is one of the most unsettling things the physics of this universe has ever forced a human being to consider. There is a map in the world that has never been drawn, but that physicists believe exists. It is not a map of continents or ocean floors. It is a map of everything that has ever happened and everything that will ever happen, laid out simultaneously in a single four-dimensional structure. Your birth is on this map. Your childhood is on this map. The conversation you had this morning is on this map. And somewhere further along the coordinate system, already plotted, already fixed, already as real and permanent as any point in the past, the moment of your death is on this map. You have not reached it yet. But it is there, not waiting, not pending, not contingent on what you do between now and then. Simply there, already existing, already real. As unalterable as the moment Julius Caesar crossed the Rubicon, or the moment the first human being looked up at the night sky and wondered what the lights were. This is the block universe, and it is not a fringe idea entertained by rogue philosophers in the margins of science. It is the interpretation of space-time that follows most directly and most honestly from the equations that Einstein gave us, and that every precision experiment in the last century has confirmed. Physicists call it eternalism. The idea that all moments in time, past, present, and future exist with equal and permanent physical reality, laid out in a four-dimensional geometric structure that does not change, does not flow, and does not prefer any one moment over any other. To understand why the physics forces us here, we need to take the discoveries of the previous section and press them to their logical conclusion. We established that time is not universal. Different observers moving at different velocities genuinely experience different rates of time. We established that there is no universal now, that simultaneity is relative, and that the present moment is not a feature of the universe, but a local, observer-dependent artifact. And we established that Einstein himself described the distinction between past, present, and future as a stubbornly persistent illusion. Now, we need to ask the structural question. If different observers in relative motion have different nows, if there is no single slice of space-time that deserves the title of the present, then what does this tell us about the relationship between past and future? And the answer is the one that most people spend their lives avoiding. It tells us that the future is just as real as the past. Here is the argument laid out in its starkest form. Take two observers. Call them Anna and Bruno. Anna is standing still on Earth. Bruno is moving away from Earth at a significant fraction of the speed of light. They are far apart. Millions of light years separate them, due to the relativity of simultaneity, which we established is a genuine geometric feature of space-time and not a matter of incomplete information. What counts as now for Anna and what counts as now for Bruno are genuinely different. The slice of space-time that Anna calls the present includes events that, from Bruno's reference frame, have not happened yet. Events that are in Bruno's future are simultaneous with Anna's present. Now, here is the critical step. We generally consider the past to be real. We consider events that have already happened to have definite existence. They occurred. They are fixed. They are part of the permanent record. So if Anna's present includes events that are in Bruno's future, and if Anna's present is real in the way that the past is real, then Bruno's future is also real. It has to be. Because if it were not real, if the future were genuinely non-existent or merely potential, then Anna and Bruno would be disagreeing not just about timing, but about existence itself. Some things would exist from one perspective and not exist from another, and that leads to an incoherence the physics cannot tolerate. The only way to make the relativity of simultaneity consistent with a coherent picture of reality is to accept that all events, past, present, and future, exist with equal reality. There can be no privilege now that divides the real from the unreal. There can be no moment at which the future snaps into existence and the past fades out of it. The entire four-dimensional structure must exist all at once, complete and permanent, the way a sculpture exists all at once rather than coming into being sequentially as you walk around it. This is what physicists and philosophers mean when they talk about the block universe. It is a universe in which time is genuinely analogous to space. Just as every point in space exists, whether or not you are currently located there, every point in time exists whether or not you are currently experiencing it. The year 1983 exists. It is real. The year 2047 exists. It is real. You are simply not at those coordinates right now. But your absence from a location does not make the location unreal, and your not yet having reached a future moment does not make that moment unreal either. The philosopher Hilary Putnam made this argument with precise rigor in 1967, showing formally that the combination of special relativity and the reality of the present moment logically entails the reality of all moments. His paper was not a piece of speculative metaphysics. It was a logical derivation from established physics, and it has never been refuted, not because physicists have not tried, but because the argument is sound. Now let us follow this to the place most people do not want to go. If the future is real in the same way the past is real, if the block universe is the actual structure of space-time, then the moment of your death already exists. It is already there, a fixed coordinate in the four-dimensional fabric, as permanent and unalterable as your childhood. You have not reached it yet from your local perspective. Your consciousness is currently tracing a path through the block that has not arrived at that coordinate, but the coordinate is there. It was always there. From outside the block, if such a perspective were possible, you would see your entire life laid out simultaneously. Birth, childhood, every decision you ever made, every person you ever loved, and the moment when it ends, all existing together in the same unchanging structure. This means something profound and terrible about the nature of anticipation and fear. When you worry about the future, when you feel anxiety about what might happen, when you hope that things will turn out well, you are responding to something that, if the block universe is correct, is already determined. Not in the sense of being caused by prior events, though that may also be true, but in the sense of already existing. The future you are anxious about is not a cloud of possibilities that has not yet resolved. It is a fixed point that you are approaching without being able to deviate from. The choices you feel yourself making, the decisions that seem to branch the future in one direction rather than another, these too are already in the block. The choice you are going to make next week is already there, already fixed, already real. You simply have not reached that coordinate yet. Your experience of deliberating, of weighing options, of feeling the future as open and malleable, is itself a feature of the block. It is what it looks like from the inside when consciousness traces its path through the four-dimensional structure. But from outside the block, there is no deliberation. There is only the fixed path, the complete trajectory, already drawn. This is a version of determinism so total, so geometrically complete, that it makes classical clockwork determinism look mild. In classical determinism, the future is fixed because prior causes inevitably produce specific effects. But there is at least a sense in which the future is being generated, produced, created by the cascade of causes rolling forward from the past. In the block universe, the future is not being generated. It already exists. It was never being generated. The entire history of the universe, from beginning to end, was always there, complete and static. And what we experience as the flow of time is simply a local perspective moving through a structure that never actually moves. Many physicists who work with general relativity on a daily basis find the block universe description unavoidable. The physicist Brian Greene, who has spent decades thinking carefully about the implications of relativity, has written that the block universe seems to be what the math is telling us, as uncomfortable as that is. Carlo Rovelli, one of the founders of loop quantum gravity and a physicist who has written more carefully about the nature of time than almost anyone alive, describes the block universe as the most natural reading of what relativity reveals, while also recognizing it as profoundly at odds with everything we experience. The disconnect between the physics and the experience is the key thing to hold in mind here. We experience time as flowing. We experience the present as special. We experience the future as genuinely open. And simultaneously, the best physical theory we have for the large-scale structure of the universe tells us that none of those features correspond to anything in the underlying reality. The flow is not there. The special present is not there. The open future is not there. What is there is a static, four-dimensional geometric structure in which all of it already exists. How can we reconcile this? How do we explain the experience of flowing time if the physics says time does not flow? The answer that most physicists point toward involves entropy and the second law of thermodynamics, which we will examine in detail shortly. But there is a more immediate answer that deserves attention here, because it deepens rather than resolves the strangeness. The experience of flowing time might itself be a feature of the block. It might be what it feels like, from the inside, to be a conscious system tracing a particular path through the four-dimensional structure. The flow is not a property of space-time. It is a property of the experience of being a particular kind of information processing system embedded in space-time and moving through it in one direction due to thermodynamic constraints. Think about what it would mean to be a character in a novel. From outside the novel, every moment of that character's life exists simultaneously on the pages. Page 1 and page 500 are both equally real, both equally present to the reader who holds the book. But from inside the novel, from the character's perspective, time flows. Events happen. The past is gone. The future is unknown. The character experiences a linear journey through a structure that, from outside, is static and complete. We may be in exactly this position. Not characters in a literal novel, but conscious systems embedded in a four-dimensional structure, experiencing our path through it as linear and flowing, while the structure itself is complete and static. Our experience of time passing is not evidence that time is passing in any absolute sense. It is evidence of what it is like to be a local consciousness tracing a world line through the block. This is the conclusion that the physicist and cosmologist Paul Davies has argued with great care over many decades. Davies points out that the block universe does not eliminate the experience of time. It explains it. The experience of flowing time is a real phenomenon. It is just not evidence for what we think it is evidence for. It is evidence for the structure of consciousness and the direction of thermodynamic processes, not evidence for a flowing, objective present in the universe itself. But let us push into territory that Davies and others find more troubling, because the block universe does not just affect your future, it affects your past in a way that should be equally unsettling, if not more so. We tend to think of the past as fixed. What's done is done. The past cannot be changed. And in one sense, the block universe confirms this absolutely. Of course, the past cannot be changed. It exists. It is there. A permanent part of the four-dimensional structure. Trying to change the past would be like trying to change a point on a map. The point is there. It does not respond to your wishes. But here is what we do not normally notice. The past's fixed quality, the thing that makes it feel inviolable and permanent, is exactly the same property that the future has in the block universe. The future is fixed not in the sense of being predetermined by prior causes, though that may also be the case. The future is fixed in the sense of already existing, in the sense of being as real and as permanent as the past. You feel that you can affect the future and cannot affect the past. But in the block, both are equally beyond your reach. You are tracing a path that is already complete. Your sense of agency, of genuine causal power over what comes next, is one more feature of the experience of moving through the block, not evidence of actual openness in the structure itself. Einstein was aware of this implication, and it weighed on him. When his closest friend Michel Besso died, Einstein wrote that Besso had preceded him by a little out of this strange world, and that this meant nothing. Because for physicists, the past, present, and future are equally real. He was not offering a cold comfort, he was making a physical claim. Besso still existed in the block. His death was a coordinate. His life was a set of coordinates. The geometry of space-time contained all of it, permanently, and Einstein saw no reason, based on the physics, to regard the fact of Besso's death as ontologically different from the fact of Besso's life. Both were simply there, in the block, equal in their reality. This is a genuinely strange form of solace, if it is solace at all. Your loved ones who have died still exist in the block. They exist at those coordinates. They are as real, in the geometric sense, as they ever were. You have simply moved forward along your world line to coordinates where your path and theirs no longer intersect. But they are there, as permanent as stone, as fixed as mathematics, as real as the past that you have always trusted to have once genuinely existed. Whether this offers any comfort depends entirely on what you think reality requires. If existence means something only when it is current, only when it is happening in a present moment, then the block universe is a cold and empty picture. But if existence means being part of the permanent structure of space-time, being a coordinate in the four-dimensional geometry that underlies everything, then nothing and no one ever truly ceases to exist. They simply recede behind you on your world line, as the origin of a journey recedes behind a traveler who cannot turn around. Now let us address the most urgent objection to the block universe, the one that physicists themselves press most forcefully. It goes like this: general relativity, from which the block universe most naturally follows, is not a complete theory. It breaks down at the quantum scale. We do not have a successful quantum theory of gravity, and quantum mechanics, particularly in its orthodox interpretations, seems to say something very different about the nature of time and the nature of the future. In quantum mechanics, outcomes are genuinely probabilistic. Before a measurement is made, a particle does not have a definite position or spin. It exists in a superposition of multiple possible states. The future, in this picture, seems genuinely open, not just unknown to us, but ontologically undecided. The block universe, with its fixed and already existing future, seems to contradict this directly. This tension is real. It is one of the deepest unresolved problems in physics. On one side, general relativity describes space-time as a complete four-dimensional block in which every event exists simultaneously. On the other side, quantum mechanics describes a universe in which the future is genuinely probabilistic and the act of observation plays a fundamental role in determining outcomes. These two frameworks, the two most successful and experimentally confirmed theories in the history of science, cannot both be completely right in their description of time. They contradict each other at this fundamental level, and we do not yet know how to reconcile them. Some physicists, working on approaches to quantum gravity, have proposed that time in the block universe is only an approximation, that at the deepest level, the quantum nature of reality introduces genuine openness and indeterminacy that the smooth block of general relativity conceals. Others argue the opposite, that the many worlds interpretation of quantum mechanics, in which every quantum outcome occurs in a branching of the wave function, is actually the most natural quantum realization of the block universe, just one in which the block is branched and multidimensional rather than a single linear thread. What is not in serious dispute is that the structure of space-time, as described by general relativity, the framework confirmed by a century of extraordinarily precise experiments, is most naturally interpreted as a four-dimensional block in which past, present, and future exist with equal reality. The questions are about how quantum mechanics modifies this picture, not about whether the block picture is the right starting point. And here is what that means for the experience you are having right now. You are moving through a structure. You are tracing a path through a four-dimensional geometry. Everything behind you on that path is real. Everything ahead of you on that path is, at minimum in the relativistic description, equally real. The open, fluid, malleable future that you feel yourself steering through is, in this picture, something more like a corridor you have not yet walked down, but that is already built. The physicist, Lee Smolin, has argued passionately against the block universe, insisting that the future is genuinely open and that time is real in a way the block universe denies. His argument is that the block universe drains physics of its explanatory power and reduces the universe to something static and dead. He may be right that something important is missing from the block picture, but he has not. And physicists generally acknowledge this, found a way to make the mathematics of relativity compatible with a genuinely open future. The block is what the equations give you. Arguing against it requires showing that the equations are wrong in some fundamental way, and that evidence has not yet materialized. So here is where we stand at the end of this section. We have followed the physics of space-time to one of its most uncomfortable destinations. We have established that the relativity of simultaneity logically requires the equal reality of all moments. We have seen that the block universe follows naturally and directly from the structure of general relativity. We have grappled with the implication that the future exists as fully as the past, that your death is already a coordinate in the geometry of space-time, and that the experience of a flowing present is a local phenomenon produced by consciousness moving through a static structure, not evidence of anything genuinely flowing in the universe itself. The block universe does not yield to the force of intuition simply because intuition finds it unbearable. The physics that produced it, the same physics that corrects GPS satellites daily and correctly predicted the age difference between traveling twins, does not leave room for negotiation on this point. The four-dimensional structure is what the equations give you. The equal reality of all moments is what the relativity of simultaneity demands. And the sense that the present is uniquely real, that the past is gone and the future has not yet arrived, is what the brain assembles in order to function inside this structure. It is not what the structure itself contains. The universe does not divide neatly into what has happened, what is happening, and what will happen. It divides into a complete four-dimensional structure in which all of it simply is. The past is not more real than the future. The future is not less fixed than the past. And you, right now, feeling the present moment surround you like a room, are standing inside an experience that the universe itself does not share. But this leaves a question so pressing, so unavoidable, that we have to address it before we can go any further. If the block universe is static, if nothing actually flows or changes, then why does our experience have such a powerful and undeniable direction? Why do we remember yesterday and not tomorrow? Why do broken eggs not reassemble themselves? Why does the universe appear to move relentlessly from order to chaos rather than the other way around? The answer lies in entropy, and in the most extraordinary initial condition the universe has ever been in. And in a set of physical laws that are, at their fundamental level, completely blind to the difference between past and future. The arrow of time is not written into the laws of nature. It is an accident, a colossal, universe-shaping, existence-enabling accident. And understanding it will crack the picture open in ways that are even more disturbing than anything we have found so far. Drop a glass. It falls, shatters, and scatters across the floor in 1,000 fragments. You sweep up the pieces. You put them in a bag, you throw the bag away. Every person who has ever lived on this planet has had an experience like this, and every single one of them has understood at the deepest intuitive level that what just happened cannot be undone. Not because you lack the skill or the patience to reassemble the glass, but because the universe does not work backward. The shards do not leap off the floor, spin through the air, and reconstitute themselves into a smooth, intact glass sitting on the edge of the table. That direction, that sequence from intact to broken, from ordered to scattered, from clean to chaotic, feels like one of the most fundamental facts about reality. It feels like the very heartbeat of time. But here is what the physics actually says. There is no law of nature that forbids the shards from reassembling. Not a single one. Almost every fundamental equation in physics, from Newton's laws to Einstein's field equations to the Schrödinger equation of quantum mechanics, is time-symmetric. The one known exception is the weak nuclear force, which exhibits a tiny asymmetry, but this effect is so vanishingly small that it cannot account for the powerful directional arrow we experience. The overwhelming machinery of physics runs identically in both directions. Run any of them forward, and they give you a valid physical process. Run any of them backward, and they give you an equally valid physical process. The mathematics does not know the difference between a film played forward and a film played in reverse. At the level of fundamental physics, there is no arrow. There is no before and after. There is only the structure of space-time and the equations that describe it, and those equations are perfectly, symmetrically indifferent to direction. This is one of the most extraordinary and least appreciated facts in all of science. The thing that feels most certain about the universe, the direction of time, the sense that the past is fixed and the future is open, the fact that glasses shatter and never unshatter, is not written into the fundamental laws of nature. It is not a law at all. It is a tendency, a statistical preference, a colossal, overwhelming, universe-spanning bias toward one direction that emerges not from any fundamental principle, but from the specific conditions the universe happened to be in when it began. To understand this properly, we need to understand entropy, not as a vague word meaning disorder, though that captures part of it, but as a precise physical quantity with a mathematical definition that reveals something profound about the structure of reality. The Austrian physicist Ludwig Boltzmann was the man who gave us this understanding, and it cost him enormously. He worked in the late 19th century, in an era when many physicists still doubted the existence of atoms. He was a man of extraordinary intellectual passion and corresponding fragility, and the resistance to his ideas drove him to a despair from which he never fully recovered. He died by his own hand in 1906, without knowing that his insights would become one of the pillars of modern physics. His epitaph reads simply with the equation he derived for entropy, a fitting monument for a man who saw so clearly and was so relentlessly disbelieved. What Boltzmann understood was this: any physical system can be in an enormous number of different microscopic configurations. Take a box of gas molecules. At any given moment, each molecule has a specific position and a specific velocity. The total number of different ways those molecules could be arranged, the total number of distinct microscopic configurations that all look the same from the outside because they have the same overall temperature and pressure, is called the number of microstates. Entropy is essentially a measure of this number. High entropy means there are many microscopic configurations that correspond to the same macroscopic appearance. Low entropy means there are very few. A hot gas confined to one corner of a box has low entropy. There are relatively few ways for all the fast-moving molecules to be clustered in one corner while the other corner stays empty. When you remove the barrier and let the gas spread throughout the box, it reaches high entropy. There are vastly more ways for the molecules to be spread evenly throughout the whole volume than there are for them all to be in one corner. The system has moved from a rare, special configuration to a common, typical one. And because typical configurations are so overwhelmingly more numerous than special ones, the system is astronomically more likely to be found in a typical state than a special one. This is the second law of thermodynamics. Entropy increases, not because there is a law demanding it, but because high entropy states are so fantastically more common than low entropy states that any system left to evolve randomly will almost certainly move toward higher entropy. Not because it has to, because the odds are stacked so overwhelmingly in that direction that the alternatives are, for all practical purposes, impossible. Now, apply this to the glass. An intact glass sitting on a table is a low entropy state. The atoms of the glass are arranged in a very specific, highly ordered configuration. A shattered glass spread across the floor is a high entropy state. There are vastly more ways for those atoms to be arranged in a scattered, broken configuration than in an intact one. So, when the glass falls, it moves from a low entropy state to a high entropy state. And the reverse, shards reconstituting into an intact glass, would require moving from a high entropy state back to a low entropy state. This is not forbidden by the fundamental laws. It is simply so statistically improbable that it effectively never happens. The number of ways you could arrange the atoms of a shattered glass in the configuration of a perfectly intact glass compared to the total number of possible scattered configurations is so small that if you waited longer than the current age of the universe by many, many orders of magnitude, you still would not expect to see it happen. The arrow of time is the arrow of increasing entropy. The direction from past to future is the direction from low entropy to high entropy. And your memory of the past, your ability to remember yesterday but not tomorrow, is a direct consequence of this entropic arrow. Here is how. Memory requires records. A record is a low entropy structure, a physical arrangement of matter that carries information about a previous event. For a brain to form a memory of an event, the event must cause a change in the brain's physical state, and that change must be more ordered, more information-rich, more specifically structured than the random thermal noise of the brain in the absence of that event. Memory formation is a process of creating a low entropy record, and crucially, that process only makes physical sense in a universe where entropy is increasing. A record created in the past, when entropy was lower, can persist into the future, when entropy is higher. But you cannot have a record of the future, a low entropy structure created by a future event, because the future has higher entropy than the present, and high entropy states do not spontaneously encode information about lower entropy states that come later. Your memory points toward the past because the past had lower entropy than the future. The arrow of your memory and the arrow of entropy are the same arrow. And the arrow of time, as you experience it, the sense that the past is fixed and known and the future is open and uncertain, is a direct consequence of the entropic gradient that runs through the universe from its extraordinary beginning to its eventual end. But now we have to ask the question that Boltzmann himself found deeply troubling. If entropy increases because high entropy states are more common, and if the laws of physics are time-symmetric, then why is the past low entropy? Why did the universe begin in such an extraordinary state of low entropy? Why is the glass intact in the past and shattered in the future rather than randomly fluctuating in both directions? This is known as the past hypothesis. It is the name the philosopher David Albert gave to the assumption that the universe began in an extremely low entropy state. And it is called a hypothesis because, strictly speaking, the second law of thermodynamics alone does not explain it. The second law tells us that entropy increases going forward. But a time-symmetric law applied to a randomly chosen present state would predict that entropy increases going backward into the past as well. If you know only the current state of the universe and the time-symmetric laws, your best prediction is that the universe was also high entropy in the past. The fact that the universe had extraordinarily low entropy at the beginning, The fact that the Big Bang produced a state of such extreme order and uniformity, the fact that there is an arrow at all, pointing consistently from a structured past to a chaotic future, requires an explanation that the laws of physics themselves do not supply. It requires an assumption about initial conditions, an assumption that the universe started in a configuration so special, so rare, so precisely ordered that even calling it improbable does not capture the scale of its unlikelihood. The physicist Roger Penrose calculated the probability of the Big Bang producing a universe with the low entropy we observe. The number he arrived at was 10 raised to the power of 10 raised to the power of 123. Written out, that number would require more digits than there are atoms in the observable universe. The initial state of the universe was not just unlikely, it was so catastrophically improbable that it seems to demand an explanation that physics has not yet provided. Why did the universe begin in such an extraordinary state? Nobody knows. This is not a matter of incomplete data or insufficient computing power. It is a genuine open question at the frontier of physics. Some cosmologists, like Sean Carroll, have proposed that our universe is part of a larger multiverse in which low entropy beginnings arise naturally from quantum fluctuations in an eternal background. Others, like Penrose himself, have proposed that the universe undergoes cycles, each ending in a heat death that becomes the low entropy beginning of the next. These are serious proposals, explored with serious mathematics. None of them have been confirmed, and the mystery of why the universe began in a state of such extraordinary order remains one of the deepest unsolved problems in all of science. But here is what makes this mystery so philosophically devastating: the arrow of time, the feature of the universe that makes your life feel like a journey rather than a static block, that makes memory possible, that makes causality feel like it flows from past to future, is entirely dependent on this mysterious initial condition. The arrow is not built into the laws. It is an accident of how things started. Remove the low entropy beginning, allow the universe to start in a typical high entropy state, and there is no arrow. Events flow in all directions equally. Memory becomes impossible. Causality loses its directional character. The sense that the past is behind you and the future is ahead of you, a feature so fundamental to your experience that questioning it feels absurd, turns out to depend entirely on an initial condition whose origin physics cannot yet explain. This should make you profoundly uncomfortable, because it means that the temporal structure of your experience, the sense of being in a moving present, of remembering a past and anticipating a future, of existing in a universe that has a clear before and after, is not a consequence of fundamental physics. It is a consequence of a cosmic accident, a statistical fluke so extreme that it should not exist, did not need to exist, and yet somehow does exist, producing the universe you live in and the arrow of time that makes your experience of it feel coherent. Now let us push into the territory that most popular accounts of entropy stop short of, because the time symmetry of the fundamental laws has an implication that goes beyond the direction of entropy. It has an implication for the nature of causality itself. We feel causality as profoundly directional. The past causes the future, a thrown rock causes a broken window, a decision causes an action, the cause always precedes the effect. This feels as certain as anything can feel. But in a universe where the fundamental laws are time-symmetric, causality is not a fundamental feature. It is another emergent property of the entropic arrow. Think about what a cause actually is in physical terms. A cause is an event at a low entropy boundary condition, an event that constrains the subsequent evolution of a system and reduces the number of possible future states. When you throw a rock at a window, the event of throwing constrains what happens next. It dramatically reduces the number of possible future states of the window to those involving broken glass. The cause and effect relationship is real, but it is not written into the fundamental equations. The equations would be equally valid if the window shattered and sent a rock flying backward into your hand. The reason that never happens is entropy. The reason causality has a direction is entropy. The reason the universe feels like a place where the past causes the future rather than the future causing the past is entropy. In the fundamental laws, there is no cause and effect. There is only correlation across time. The directionality we assign to causality, the sense that the rock caused the window to break rather than the broken window causing the rock to fly, is something we impose on the equations based on the thermodynamic arrow. It is the difference between a boundary condition in the past, which is constrained and specific, and a boundary condition in the future, which is typically not specified and therefore seems open. Julian Barbour, a physicist who has spent decades thinking more carefully about time than almost anyone, has argued that time itself, in its fundamental form, does not exist. His model describes the universe not as a four-dimensional block, but as a static space of possible configurations he calls Platonia. Each point in Platonia is a complete snapshot of the universe, a specific arrangement of everything that exists. What we call time is the experience of moving through this space of configurations, tracing a path from lower to higher entropy configurations. There is no genuine flow, there is no genuine passage. There are only the configurations themselves and the entropic gradient that makes one direction of travel through them overwhelmingly more probable than the other. Barbour's model is controversial and not accepted by the majority of physicists, but the question it addresses is the right one. If the fundamental laws are time-symmetric, if there is no preferred direction built into the equations, then what exactly is flowing when we say time flows? Barbour's answer is nothing. Nothing is flowing. The experience of temporal flow is what it feels like from the inside to be a complex, entropy-generating, memory-forming system tracing a path through a static configuration space. And here is the piece that should freeze you in place. If the arrow of time is a consequence of the entropic gradient, and if that gradient depends on the universe starting in a low entropy state, and if the low entropy state of the beginning is not explained by any known physical law, then the arrow of time is built on a foundation that physics cannot justify. The most undeniable feature of your experience rests on a mystery. The direction of causality, of memory, of your sense of moving from past to future, all of it is downstream of an initial condition that should not exist and that nobody can explain. Sean Carroll, one of the physicists most deeply engaged with the problem of time and entropy, has framed this with characteristic directness. He argues that the reason the past is different from the future, the reason we remember one and not the other, the reason the universe does not look the same in both temporal directions, is not because of any fundamental law. It is entirely because we happen to live in the aftermath of an extraordinarily low entropy beginning. And the fact that we cannot explain why the beginning was low entropy is not a detail. It is the central mystery. It is the question behind the question. It is the reason the arrow of time exists, and it is a question that physics in its current form cannot answer. But there is one more layer to excavate here, one that many discussions of entropy and the arrow of time skip over because it is the most disorienting of all. We have established that the fundamental laws are time-symmetric. We have established that the arrow of time is a product of entropy and initial conditions rather than fundamental physics. And we have noted that in the fundamental equations, there is no distinction between past and future. Now consider what this means when you look at a specific physical interaction, not the large-scale evolution of galaxies or the decay of complex biological organisms, but a single particle interaction. An electron emitting a photon, two quarks exchanging a gluon, a radioactive nucleus emitting an alpha particle. In each of these cases, if you filmed the event and played the film backward, the reversed version would be physically valid. It would obey all the same laws. It would be indistinguishable. at the level of fundamental physics, from a legitimate physical process. This means that at the level where reality is most fundamental, where the actual machinery of the universe is operating, there is no arrow. There is no before and after. There is no cause preceding effect. There are only interactions, and those interactions are equally valid in both temporal directions. The arrow you experience, the one that makes memory possible and causality directional and time feel like a river, is a macroscopic phenomenon. It is what emerges when you pile up an unimaginably large number of these individually reversible microscopic interactions and let statistics do its work. Your sense of being inside a flowing present, embedded in a past that is gone and approaching a future that has not arrived, is a statistical average of an inconceivably large number of individually timeless microscopic events. It is an emergent property of complexity and scale, not a feature of the underlying reality. The river of time that you feel yourself floating on does not exist at the level of the current, it exists at the level of the ocean, and the ocean itself is made of water molecules that do not know which way the current flows. This is where entropy leaves us. In a universe whose laws are timeless, whose arrow of time is a statistical accident, whose causality is an emergent approximation, whose past is special not because of any fundamental principle, but because of an initial condition so improbable that it strains the concept of probability itself, and whose experience of flowing time, that most certain and immediate of all sensations, is a story that entropy tells a complex enough system about which end of the statistical gradient it is on. The clock on your wall is ticking forward. Every tick is bringing the universe to a slightly higher entropy state. Every tick is moving you further from the extraordinary beginning that made the arrow possible. And at the end of this process, when entropy has reached its maximum and the universe settles into the stillness of heat death, the arrow of time will dissolve. There will be no past and no future. There will be no before and no after. There will be no memory and no anticipation. There will only be the equilibrium of a universe that has finally, after billions upon billions of years, reached the high entropy state that the laws of physics always said was overwhelmingly most probable. But that ending raises a question so disturbing that physicists have spent decades trying to avoid it, because in a universe of infinite time and maximum entropy, quantum fluctuations do not stop. They cannot stop. And the implications of what those fluctuations can produce, left to operate for long enough in a universe of maximal disorder, lead somewhere that makes the block universe and the entropic arrow feel almost comforting by comparison. They lead to the question of whether time is fundamental at all, whether the equations that describe the deepest level of reality contain time as an ingredient. And the answer that the mathematics gives, the answer written into the most fundamental equation we have for the quantum state of the entire universe, is the most disturbing answer in this entire story. The answer is no. In 1967, two physicists named John Wheeler and Bryce-DeWitt wrote down an equation. It was not a simple equation. It took years of painful theoretical work to derive, combining the machinery of quantum mechanics with the geometric language of general relativity in an attempt to do something nobody had successfully done before. Describe the quantum state of the entire universe. A single equation that would capture everything. The wave function of the cosmos itself. The complete quantum description of all matter, all energy, all geometry, all of existence from beginning to end. They wrote it down, they checked it again, and then they found something inside it that neither of them had expected. Something that, once seen, could not be unseen. Something that has haunted theoretical physics ever since, and that sits at the center of the deepest unsolved problem in all of science. The equation had no time variable. Not a missing term that needed to be filled in. Not a gap in the derivation. The time variable was structurally absent. The most fundamental equation ever written for the quantum state of the entire universe, the equation that was supposed to describe how reality evolves, how the cosmos changes from moment to moment, did not contain time as an ingredient. The universe, at the deepest level the mathematics could reach, appeared to be timeless, static, a quantum state that simply is, without any mechanism for becoming, without any variable representing the passage from one moment to the next. Wheeler himself called this the problem of time. It remains one of the most profound and unresolved issues in theoretical physics today, and to understand why it matters, why it is not simply a technical glitch in an incomplete equation but a genuine signal about the nature of reality, we need to follow it carefully, because it leads somewhere that makes everything we have discussed so far look like a gentle introduction. We have already established that the fundamental laws of physics are time-symmetric, that they work equally well in both temporal directions. We established that the arrow of time is an emergent property of entropy rather than a fundamental feature of the equations. We established that the block universe interpretation of general relativity places past, present, and future on equal ontological footing. All of these discoveries push time from the center of physics toward its periphery. They suggested that time, as we experience it, is not what it appears to be. But the Wheeler-DeWitt equation goes further. It does not just challenge the direction of time or the special status of the present moment. It challenges whether time is a fundamental ingredient of reality at all. And the distinction between those two claims is enormous. A universe where time exists but flows in both directions is strange. A universe where time does not fundamentally exist, where it is not built into the deepest level of physical law but emerges from something more primitive, is something else entirely. It is a universe where the most basic framework of your experience, the sense of existing within time, of being a thing that persists and changes and moves through moments, is not reflected in the underlying structure of what is real. To understand the Wheeler-DeWitt equation and why it lacks a time variable, we need to understand what it was trying to do. General relativity describes the geometry of spacetime as a dynamic entity. It curves and bends in response to matter and energy. The geometry of space evolves over time, in the sense that the shape of the spatial universe changes as the cosmos expands and structures form. Quantum mechanics, on the other hand, describes the evolution of quantum systems using a wave function that changes according to the Schrödinger equation, which explicitly contains a time variable. Time in quantum mechanics is a fixed, external background against which quantum states evolve. The problem is that in general relativity, there is no fixed external background. Space-time itself is dynamic. It is part of the system being described. When you try to combine quantum mechanics with general relativity, when you try to write a quantum equation for the geometry of space-time itself, you run into a fundamental conflict. Quantum mechanics needs a fixed time background to define evolution. General relativity says there is no fixed time background. Time is part of the geometry, and the geometry is what you are trying to quantize. Wheeler and DeWitt's attempt to resolve this conflict produced an equation in which the time variable effectively cancels out. The wave function of the universe does not evolve with respect to any external time parameter, because there is no external time parameter. The universe is a closed system. There is nothing outside it against which its evolution could be measured. The total quantum state of the cosmos in this framework is frozen, static, timeless. This result struck many physicists as deeply wrong. It seemed to be saying that nothing happens, that change is an illusion, that the universe is a single, static quantum state, and the extraordinary richness and dynamism of everything we observe, galaxies forming, stars burning, life evolving, consciousness arising, is somehow consistent with an underlying reality in which time does not pass. But a growing number of physicists, rather than dismissing the Wheeler-DeWitt equation as a failure, began asking a different question. What if it is right? What if time genuinely does not exist at the fundamental level? And if so, where does time come from? How does the experience of time emerge from a timeless foundation? This is the question that has driven some of the most creative and disturbing work in theoretical physics over the last several decades. And the answers that have emerged are, depending on your disposition, either deeply beautiful or deeply terrifying. In most cases, both simultaneously. One of the most influential proposals came from the physicist Don Page and his collaborator William Wouters in 1983. Their idea is called the Page-Wouters mechanism, and it is elegant in a way that makes your head spin when you follow it to its conclusion. The proposal is this: time does not exist at the level of the universe as a whole. The total quantum state of the universe is indeed timeless, as the Wheeler-DeWitt equation suggests. But time emerges from the correlations between different parts of the universe. Specifically, time is what you measure when you use one quantum system as a clock to describe the evolution of another quantum system. Think about what a clock actually is. It is a physical system that changes in a regular, predictable way. The hands move, the atoms oscillate. The quantum state of the clock evolves in a sequence of configurations that we interpret as the passage of time. But crucially, the clock's evolution is not absolute. It is relational. The clock measures time relative to the rest of the universe. Time, in this picture, is not a background against which things happen. It is a relationship between things. It is the correlation between the state of a clock and the state of everything else. In the Page-Wouters framework, if you look at the total wave function of the universe from the outside, there is no time. Everything is static. But if you are inside the universe, if you are a quantum system entangled with other quantum systems, you will observe those other systems to evolve in a coherent, time-ordered sequence relative to yourself. The experience of time passing emerges from quantum entanglement. It is what it feels like from the inside to be a part of a timeless quantum system that is correlated with other parts of itself. This idea was initially treated as a mathematical curiosity. But in 2014, a team of physicists led by Ekaterina Moreva performed the first genuine laboratory demonstration of the Page-Wouters mechanism. They created an entangled quantum system in which one part acted as a clock and the other acted as an evolving system. From an external perspective, the whole system was in a static, timeless quantum state. But from the perspective of the clock subsystem, the other part of the system appeared to evolve in a time-ordered way. Time appeared to emerge from the entanglement, not from any fundamental temporal ingredient, but from the correlations between parts of a timeless whole. This is an extraordinary result. It suggests that the time you experience, the sense of moments passing, of the present giving way to the future, is not evidence that time is fundamental. It is evidence that you are entangled with a universe of other quantum systems, and that the correlations generated by that entanglement produce the experience of temporal evolution. Time is not the stage on which the universe performs. Time is a relationship. It is what entangled quantum systems look like to each other from the inside. Now pause and let the full strangeness of this settle. You experience time passing right now. You feel the present moment as vivid and immediate. You feel yourself moving from one instant to the next. The Page-Wouters mechanism says that this experience is generated by quantum correlations between the systems that make up your brain and body and the rest of the universe. If you could somehow step outside the universe, if you could view the total quantum state from an external vantage point, you would see no time. You would see a static, timeless quantum configuration in which everything that has ever happened and everything that will ever happen exists simultaneously in a superposition of correlations. The experience of time passing is entirely internal to the system. It has no counterpart in the view from outside. There is no outside vantage point available to us. We are inside the system. We are made of it. Every observation we make is an internal correlation between one part of the timeless quantum state and another. And so we experience time as inevitably as a character in a book experiences the narrative, even though from outside the book the entire story exists simultaneously on all the pages at once. Carlo Rovelli, who has thought about the nature of time with extraordinary depth and has written about it with a clarity that few scientists achieve, takes a related but distinct approach in his thermal time hypothesis. Rovelli argues that time as we experience it is not even primarily a quantum phenomenon, it is a thermodynamic one. In a system with many degrees of freedom, the kind of complex, high-dimensional system that constitutes the universe we live in, there is a natural variable that behaves like time. It is defined by the flow of thermal energy, by the direction in which entropy increases. Rovelli, working alongside the mathematician Alain Connes, argues that what we call time is simply the thermal flow of a complex system. It is the direction in which the system is most likely to evolve, given its current state. Time is temperature. Time is entropy. Time is what a warm, complex, far from equilibrium system experiences as its energy dissipates and its entropy rises. Both of these proposals, the Page-Wooter's mechanism and Rovelli's thermal time, point toward the same radical conclusion. Time is not fundamental. It is emergent. It arises from something deeper, whether that deeper thing is quantum entanglement, thermodynamic flow, or some combination of both that we do not yet fully understand. The universe at its most basic level does not contain time as an ingredient. Time is what happens when you look at a timeless quantum system from the inside, when you are a small, warm, entangled, entropy-generating piece of a vast static quantum state, and you try to describe the correlations between yourself and everything else. This conclusion, if correct, reframes everything we have discussed in this story. We began by establishing that the present moment is a neural construction with a measurable delay. We moved to the relativity of simultaneity and the discovery that there is no universal now. We examined the block universe and the equal reality of all moments. We explored entropy and the emergent arrow of time. And now we arrive at the most fundamental level, where the equations that are supposed to describe the deepest structure of reality contain no time variable at all, and where the best proposals for explaining why we experience time suggest that it arises from quantum correlations in an underlying timeless reality. At each layer, time has retreated further from the center of physics. The present moment turned out to be a neural construction. The now turned out to be observer-dependent. The flow of time turned out to be an entropic gradient. And time itself turns out, at the deepest level we can currently reach, to be an emergent property of a timeless quantum substrate. The arrow you experience, the one that makes memory possible and causality directional, and your life feel like a journey rather than a sculpture, is not inscribed in the laws of nature. It is borrowed from a beginning, and the beginning has no explanation that physics can currently supply. What does this mean for you? For the experience of being alive, of existing inside time, of having a past that is gone and a future that is coming? It means that the framework within which your entire conscious life takes place, the structure that makes memory possible and anticipation meaningful and experience coherent, is not a feature of the universe. It is a feature of you. It is what it feels like to be a complex quantum system correlated with a vast, timeless whole, generating entropy as you go, experiencing the gradient of that entropy as the passage of time, constructing the present moment from delayed and edited neural signals, and never once, in the entire course of your life, having direct access to the timeless structure that underlies everything you experience. You are inside time the way a fish is inside water. The fish has no experience of wetness because wetness is not something that exists separately from the fish's interaction with the water. It is the interaction itself. Time is not something that exists separately from your interaction with the quantum correlations and entropic gradients of the universe. It is the interaction itself. And the fish cannot step outside the water to see what water actually is. You cannot step outside time to see what the timeless quantum state actually looks like. You are constitutionally, irreversibly embedded in the experience. Now we need to synthesize. We have covered an enormous amount of ground in this story, and it is worth pulling the threads together to see the full picture that the physics paints, because the individual discoveries are disturbing on their own, but their combination is something else. It is a picture of time so alien to ordinary human intuition that it requires a fundamental revision of what you think you are and where you think you exist. The present moment, as we established, is a construction of the brain assembled from signals arriving at different times, with active editing, with a half-second delay, optimized not for accuracy but for survival. The brain does not show you when things happen. It shows you a coherent narrative of when things happen. The experience of now is a story, not a readout. Beneath that biological construction, the physics of space-time reveals that there is no universal now. The relativity of simultaneity proves that different observers in relative motion have genuinely different presence, not due to incomplete information, but due to the geometric structure of space-time itself. The present moment is not a feature of the universe. It is a feature of your reference frame. The block universe interpretation, following directly and honestly from the structure of relativity, places all moments on equal ontological footing. Past, present, and future are all equally real, all equally permanent, all equally fixed. The sense that the future is open and the past is closed is a consequence of the thermodynamic arrow, not a fundamental feature of time's structure. The arrow of time itself is a consequence of entropy, and entropy's directional behavior is a consequence of the extraordinarily low entropy initial condition of the universe. An initial condition so improbable that it strains our entire framework for thinking about probability, and whose origin remains entirely unexplained by any known physical law. The direction of time, the directionality of causality, the fact that you can remember the past but not the future, all of this rests on a mystery that physics cannot yet resolve. And at the deepest level, the Wheeler-DeWitt equation tells us that time is not a fundamental ingredient of the quantum state of the universe. The Page-Wooter's mechanism suggests that time emerges from quantum entanglement, from the correlations between subsystems of a timeless whole. Rovelli's thermal time hypothesis suggests it emerges from thermodynamic flow. All of these proposals agree on the essential point. Time is not at the bottom. Something else is at the bottom, and time is what it looks like from where we stand. What are we to make of this? What does it mean to be a human being? A conscious, time-experiencing, memory-having, future-anticipating creature, living inside an experience of time that the physics tells us has no fundamental correlate in the underlying structure of reality. One possibility, the one that most of us instinctively resist, is that the physics is incomplete, that time is real and fundamental, and that we simply have not yet found the right equations to capture it. This is a legitimate position. Many physicists hold it. Lee Smolin has argued forcefully that the timelessness of current fundamental physics is a symptom of a conceptual error, that we have been trying to describe reality from a God's eye view that no actual observer can occupy, and that a genuinely observer-relative physics would restore time to its rightful place as a fundamental ingredient of reality. His work on the principle of precedence and the reality of time is serious physics, not wishful thinking. He may be right, But the weight of the current evidence does not support this optimism. The Wheeler-DeWitt equation is not an accident. The time symmetry of the fundamental laws is not a quirk. The entropic origin of the arrow is not a detail. The Page-Wooter's experimental results are not a fluke. These are independent lines of evidence from completely different branches of physics, all pointing toward the same conclusion. Time, as we experience it, is not what it appears to be, and the physics at the deepest level we can currently reach does not contain it. The other possibility is that the physics is right, that time is genuinely emergent, and that we are faced with the task of understanding what it means to be conscious, time-experiencing beings whose most fundamental experience has no fundamental physical counterpart. This is not a comfortable position. It is not a position that offers easy consolation, but it is, for now, the most honest position available given what the evidence says. And here is the deepest implication, the one that requires sitting with its full weight rather than moving past it quickly. If time is emergent, if it arises from quantum correlations in an underlying timeless reality, then the distinction we have been drawing throughout this story between what exists and what does not, between the real present and the unreal future, between the fixed past and the open tomorrow, is a distinction that exists nowhere except in the experience of conscious systems embedded in the quantum fabric. There is no past, there is no future, there is no present, there is only the timeless quantum state of the universe, the complete wave function of everything. And there is the experience that arises when complex, entangled, entropy-generating systems like us interact with it from the inside and call the correlations they observe time. Your life from the outside, from the perspective of the timeless quantum whole, is not a journey, it is a pattern, a specific, complex, beautiful, fragile pattern of correlations in the quantum state of a universe that does not itself experience duration. Your birth and your death and every moment between them are not sequential in any fundamental sense. They are simultaneous features of a timeless structure, the way all the notes of a symphony are simultaneously present in the score, even as the performance unfolds them in sequence for the listener. You are the listener. The universe is the score. And the experience of hearing one note after another, of being carried through the music from opening to close, is not evidence that the notes are coming into being as you hear them. It is evidence that you are a particular kind of system that experiences a timeless structure as a temporal sequence. Many physicists, when pressed on what this means personally, retreat into a careful scientific neutrality. They say that these are questions about the interpretation of the mathematics, that the physics does not necessarily tell us about the nature of experience, that consciousness and its relationship to time remain genuinely open questions. This is intellectually responsible. It is also, in a certain light, a way of not fully looking at what the equations are saying. What the equations are saying is this: the universe does not have a clock. It does not have a present moment. It does not have a direction of travel. It is a timeless quantum state in which all possible correlations coexist. And in certain regions of that state, complex systems arise that are structured in such a way that they experience the correlations as temporal sequences and call that experience reality. You are one of those systems. Your experience of time is real in the sense that it is genuinely occurring, genuinely structured, genuinely the experience you are having, but it is not a window onto a fundamental feature of the universe. It is a shadow cast by a timeless structure onto the wall of your consciousness. The shadow is real. The shape it appears to have is real. But the thing casting the shadow does not itself have that shape. This is where the physics of time leaves us. Not with an answer, but with a dissolution. The question of what time is has been answered, to the extent that current physics can answer it, by showing that it is not fundamental, that at the deepest level of description we can reach, the universe does not contain it. That the experience of time, the river you have been floating on your entire life, is generated by quantum entanglement, thermodynamic gradients, neural construction, and relativistic geometry, combining to produce something that feels like the most immediate and certain feature of existence, but that has no counterpart in the underlying timeless reality. We have arrived, after descending through every layer available to us, at a conclusion that is deeply strange and cannot be made comfortable. The flow of time is an illusion generated by entropy. The present moment is a neural construction. The future is already as real as the past in the block, and time itself does not appear in the most fundamental equation we have for the quantum state of everything. Einstein called the separation of past, present, and future a stubbornly persistent illusion. He was more right than even he knew. The illusion is not just stubborn, it is structural. It is built into the architecture of consciousness by evolution, reinforced by the thermodynamic arrow, given apparent substance by the block universe's equal treatment of all moments, and finally dissolved at the quantum foundation by an equation that does not know what time is. You are a temporary pattern in a timeless structure, experiencing duration because you are the kind of system that generates entropy, forming memories because the past had lower entropy than the future, feeling the present as vivid and real because your brain constructs it half a second late and calls the result now. And beneath all of that, at the level where the actual machinery of reality operates, there is no clock, there is no arrow, there is no before or after. There is only the wave function of everything, static, complete, timeless, and utterly indifferent to the extraordinary experience of time that arises for a brief moment of cosmic duration inside the small, warm patterns that look up at the night sky and wonder where all the time has gone.